Now we are going to learn about gas exchange. So there's really two factors that determine the rate of gas exchange, and that's going to be the partial pressure gradient of the gases involved. And what that means is the difference in partial pressures. Like, for example, the alveoli partial pressure is 100 and something, and it's 40 something in the capillaries. So that pressure gradient is the difference between those pressures. So that pressure gradient or pressure difference in the gases. And then the other thing has to do with the solubility of the gases, which affects their diffusion rate. Some gases are more soluble than others. So those are the things, the pressure differences and the solubility of those gases. So I've skipped a lot of this, so I just want to focus on the figure 1512, the respiratory processes and partial pressures. So let's start with external respiration, and that's going to occur between the alveoli in the lungs and the capillaries that surround them. So let's just look at oxygen. The partial pressure of oxygen in an alveolus is 100 millimeters of mercury. In the capillary, the partial pressure of oxygen as it comes toward the alveolus from the, I should say it would be the arterial end, but anyway, it doesn't matter. As it moves toward the alveolus, the partial pressure of oxygen is 40 millimeters of mercury. So that's a difference of 60 millimeters of mercury. So oxygen is going to move from that alveolus into that capillary because the pressure is greater in the alveolus. Then we have carbon dioxide. Now, carbon dioxide has a partial pressure of 45 in the capillary and 40 in the alveolus, but that's not a big pressure gradient. But carbon dioxide is much more soluble than oxygen. So because it has that increased solubility, it doesn't need a big difference in pressure to move from the blood into the alveolus. But mainly, I just want you to know oxygen moves from the alveolus into the capillary. Carbon dioxide moves from the capillary into the alveolus. And then here's your tissues. An internal respiration, you have oxygen diffusing from your capillaries into your tissue cells. And then carbon dioxide diffusing from your tissue cells into your capillaries. And so I really just want you to know that direction that those two gases move. Then we have transport of oxygen in the blood. Oxygen is transported in the blood. 98.5% of the oxygen is transported attached to hemoglobin. 1.5% of the oxygen gas is transported, is dissolved in the plasma. There we go. Okay, so here's another place where I have to highlight this stuff. Let's see. Oh, sorry. Okay, so the amount of oxygen that is bound to hemoglobin, that once it binds to the hemoglobin, we also want it to be able to release from the hemoglobin whenever it's time for it to move into our tissue cells. So the factors that determine the amount of oxygen bound to or released from the hemoglobin molecule one is going to be the partial pressure of oxygen in the tissue cells or the tissue fluid, pH level of the fluid, and then also temperature. A low partial pressure of oxygen, low pH, and high temperature, these are the factors that will increase the release of oxygen to the tissues or increase tissue perfusion. So high temperatures, low pH, low partial pressure of oxygen. And then another thing I want you to know is the role of carbon monoxide and its role in carbon monoxide poisoning. Carbon monoxide can also bind to hemoglobin. So if it does, it blocks oxygen from binding. And that causes hypoxia, which can lead to you falling asleep and dying. All right, transport of carbon dioxide is a small percentage of carbon dioxide dissolved in the plasma, 7%, because carbon dioxide is more soluble than oxygen. So that's a higher percent than the percentage of oxygen dissolved in plasma. Then we have another small percent of carbon dioxide, 23%, can actually attach to the globin portions of the hemoglobin molecules and be transported by hemoglobin. And then 70%, the majority of carbon dioxide is converted to bicarbonate, and it's transported through the plasma as bicarbonate ions. And here is a figure that shows those percentages. It shows how carbon dioxide diffuses into the bloodstream. 93% diffuses into the red blood cells. 23% binds to hemoglobin. 70% is converted to carbonic acid, which is then converted into, this is the bicarbonate ion. And then once it has reached the alveoli, then the bicarbonate is going to be converted back into carbon dioxide in the blood plasma. All right, and then we didn't account for the 7% of carbon dioxide that remains in the plasma as dissolved carbon dioxide. So the overall reaction for the conversion of carbon dioxide into bicarbonate, it looks like this. So carbon dioxide, when it's in the presence of water, when it's dissolved in water, is converted to, this is carbonic acid, and then immediately that dissociates into hydrogen ions, and this one here, the HCO3 minus, is bicarbonate ion. And this is how the majority of carbon dioxide gas is transported in the blood, by being converted to bicarbonate ions. This is actually inside the red blood cells. So the water that combines, the carbon dioxide reacts with water in the cytoplasm of the red blood cell, not the water in the blood plasma. This figure is probably not necessary after we went over everything, but it goes through the, okay, what you're looking at on the left is the transport of carbon dioxide and oxygen between the capillaries and the alveoli. So this is external respiration here on the left, and then you see internal respiration on the right. And I mean, there's no need for us to go over that information a second time. We've already gone over it once. All right, checkpoint question 21. As you exercise, hemoglobin releases more oxygen to active skeletal muscles than it does when the muscles are at rest. It says why. Now, I haven't looked up this answer, but I know that when you exercise, you produce lactic acid, which is going to lower the pH. And if you remember, low pH causes more tissue perfusion, increased tissue perfusion, or increased oxygen to the tissues. So that could be one reason. It's probably the main reason. Now, how would blockage of the trachea affect blood pH? So if the trachea is blocked, then it's going to decrease the oxygen that's able to come in through your lungs. So it's going to decrease the oxygen that's in your blood, and the carbon dioxide can't get out either. So it's going to increase the CO2. Increasing carbon dioxide levels lowers blood pH by producing hydrogen ions. So it's going to decrease the blood pH. All right, skipping some of this. I do want to just go through chemoreceptor respiratory reflexes, some factors that are involved in control of respiratory rate. So one factor that has a very strong effect is the partial pressure of carbon dioxide. In fact, the levels of carbon dioxide in your blood, dissolved in your blood, have a greater effect and a more immediate effect than the levels of oxygen. Typically, if you have high carbon dioxide, that corresponds with low oxygen. But your chemoreceptors detect, they are stimulated more by carbon dioxide levels than oxygen levels. And increases in carbon dioxide partial pressure or concentration, which is correlated with decrease in pH. These are prime stimulators of respiratory rate increases. So it causes you to breathe faster whenever you have high levels of carbon dioxide in your blood or low pH. Okay, checkpoint question. I like this question because we have all asked this at some point in our life. If you haven't, good for you, but most of us have. I've talked to enough students over the years. So little Johnny tells his mother he will hold his breath until he turns blue and dies. Should she worry? Okay, so even though if you've ever seen a kid threaten this and you've watched them try to hold their breath until they turn blue and die, it can be scary, especially if it's a strong-willed child. She should not worry, because even if he is so strong-willed and is just able to hold his breath until like the point that he passes out, which he probably can't, but let's just say he does, what's going to happen is while he's passed out, carbon dioxide levels are going to rise inside of his body fluids. And that is going to stimulate his inspiratory respiratory centers in his pons and medulla. And they're going to send nerve impulses that will trigger those muscles of inhalation to contract. Even if he's unconscious, and so he's going to inhale. His intercostals, external intercostals, and his diaphragm are going to contract because they're going to get stimulated by the signals from the pons and the medulla. So no, she should not worry. All right. And you cannot hold your breath until you die, because that's what will happen. So respiratory performance in age, we're almost at the end here. Some emphysema is normal in aging. And remember, that increases lung compliance, but it increases it too much. And that makes it difficult to get enough air into your lungs as well. You've got to have some stiffness, in the lung tissues. Some compliance you have to have. But too much compliance is not good. Stiffening and decrease in chest movement also limit breathing, pulmonary ventilation, and decrease your vital capacity. So that is going to decrease compliance, but both things are bad and cause difficulty with breathing and gas exchange.